Tony O'Hagan mentioned this example to me once, but it's not his example originally, which is what happens if you're in a trial and you've evaluated all the evidence and a witness suddenly runs into the room and sort of says, he did it, he did the murder. And you haven't got this witness in your model. So this is not a parameter you've considered. And this seems like a very difficult situation, but actually the answer is non-parametric models, because these models consider infinite possibilities of things that can happen and are still consistent in a very interesting, exciting way. And there's been a lot of work in this area of machine learning, which Fitz can tell us about.
Thank you, Neil. All right, so good morning, everybody. So here's my rough plan of what I'm going to talk about today and tomorrow. Today I'm going to talk about some basic terminology, and then I will spend probably most of today's lecture talking about clustering, so about mixture models, which Ruben has mentioned earlier. And then I will talk a little bit about latent feature models. And tomorrow I'm going to speak on some a bit more advanced things. So essentially what I'm going to do is I'm going to talk about how we can construct new Bayesian nonparametric models. And I will try to use it as a vehicle to present some of the work that has been done in that field. In connection with that, I'm going to talk about something that I'm also briefly going to discuss today, which is exchangeability. And if we have time tomorrow, then I'm going to talk about asymptotics, on how you can theoretically evaluate how well your models perform. Okay. But today, I'm mostly going to talk about clustering, so about Dirichlet processes and models related to that. Good. So, I gave a tutorial with Yuvaite at MIPS on Bayesian nonparametrics, and if any of you have seen that tutorial, the first few slides, I think the first 3 or 4 slides are the same. But after that, I'm not just going to repeat the tutorial. Okay, okay, so here's a very simple description of what we're trying to do in statistics, a kind of cartoon picture of statistics. And that is we have a statistical model which is a probability distribution of some observation variable x, which describes our data. And that given a parameter theta. Okay, and that the fact that I'm writing that as a conditional probability here is already, in a way, a Bayesian assumption, because I'm saying I'm conditioning on a random variable here, so the parameter is a random variable, and that is exactly what characterizes the Bayesian model. And so what I mean by this here is probability of data given some parameter, and the way I would like you to think about a parameter here is to think about some kind of pattern that underlies the data. And here's an example. So this is a simple linear regression example, where the blue dots here are the data, and the red line, this linear trend here, is a pattern. So in this case, a pattern would be a linear function. And here is a slightly more sophisticated example, which is again a regression example. And again, the pattern is a function, but in this case, it's not linear anymore. And this is the kind of thing that we can do with a Gaussian process, for example, in Bayesian nonparametrics. Okay, so if we look at this picture here, what we're trying to do is we're making an assumption here, usually in Bayesian statistics or generally in statistics, which is some kind of independence assumption. Yeah? And basically what we're assuming is that there is this underlying pattern, this is this linear trend here, and then the data that we observe is basically this pattern plus some randomness. Yeah? So the points are not exactly on the red line, they scatter around the line, that is some kind of randomness. But we assume that this random deviations from the line happen independently of each other for different points. Yeah? So the assumption we're making here, the idea behind inference is that the data is underlying pattern plus some independent noise. And independent is really essential here. I would ask you to read this plus in a purely qualitative fashion. Yeah? So the noise could be multiplicative or something. I'm just trying to say this is pattern and noise. Okay? All right. And so in a if we're being Bayesian, then we assume that this pattern here is a random quantity. Yeah? That's the basic characteristic of a Bayesian model, and the distribution of that pattern is the prior distribution. What we try to compute is, when we have seen data, we try to compute the posterior, which is the distribution of this pattern given that the data looks the way it looks. Okay? All right, so now what is a non-parametric Bayesian model? In a parametric model, in statistics, a parametric model is a model which, first of all, which has parameters, of course, but it has some fine print, and the fine print is the number of parameters is fixed, or the number is at least constantly bounded with respect to sample size. So as we see more and more data, the number of parameters does not increase. Yeah? There's just a fixed number of parameters. And a non-parametric model is a model which also uses parameters, and so it's really a misnomer. But it's a model which does not match the fine print. Yeah? So a non-parametric model is where the number of parameters grows with the size of the sample. And if you think of the parameters, if you think of the number of parameters as the degrees of freedom that the model has, then this means that the model can become more and more complicated as we see more and more data. Okay. Okay, so if we want to now in Bayesian modeling, what we do is we treat the parameter as a random quantity, and we describe it by a probability distribution, right? So we have to take the parameter space and we have to put a probability distribution on that, and we call that the prior. Now, if we want to do that here, where the number of parameters is not bounded, then as we see infinitely many data points, we can't put a maximum dimension on the size of the parameter. And so we have to use an infinite dimensional space. Okay? So a non-parametric model, and this is not only true in Bayesian modeling, pretty much in general, one way to define non-parametric models is to say that it's a statistical model which has an infinite dimensional parameter space. Okay? So here's an example, simple density estimation example. And this is not a Bayesian example, this is just standard parametric versus non-parametric statistics. So in both cases, we're going to estimate a density using a Gaussian distribution, but we're going to use the Gaussian distribution in two different ways. Yeah? So here we have a bunch of data points, and we're just making a parametric assumptions and say, okay, the data is generated by a two-dimensional Gaussian distribution. So we fit in a Gaussian, say, with maximum likelihood. Okay? And we get this picture here. And you see, if there's more data coming in, that may change our estimate of the parameter, but it does not change the dimensionality of the parameter. Right? It's just a two-dimensional location parameter and a 2x2 covariance matrix. Okay, and here this is a Parsing window type estimator. So what we're doing here is each time we see a data point, we fix a Gaussian with a fixed covariance matrix and put this Gaussian at the location of the data point. Yeah? So we're setting the mean parameter of the Gaussian to the location of the data point. And we do that for every data point, and then we normalize, we add up these densities and normalize. Okay, so basically what we're doing is we're using, you can think of this as smoothing. We're doing a convolution with a Gaussian kernel, and that way we smooth the data. The data is a bunch of spikes, sharp spikes, and we smooth that with a Gaussian. Okay? And the density estimate we get that way is called a Parsing window estimator. Okay? All right, so you can see that in this case, we get one additional location parameter for each data point that we see, and the number of data points increases. As the number of data points increases, the dimension of the parameter space increases. Okay? So to accommodate this unbounded number of parameters or unbounded number of parameter dimensions, we need an infinite dimensional space. Yeah. All right, and now if we want to be Bayesian about it, if we want to put a prior distribution on that, then what we have to do is we have to put a prior distribution on an infinite dimensional space, and that is a non-parametric Bayesian model. Yeah? So the definition that we're going to use here of a non-parametric Bayesian model is a non-parametric Bayesian model is a Bayesian model on an infinite dimensional parameter space. Okay. Is that clear so far? Okay, and the interpretation here is that the parameter space, or one useful way I think to interpret it is the parameter space is the set of possible patterns that we assume can explain the data. Yeah? So in the density estimation example that we just saw, the set of possible patterns would be a set of probability distributions, right? Or a set of densities, more precisely, because we're doing density estimation. If we're doing regression, so the example on the first slide, then the pattern would be a smooth function. And if we do clustering, which we're going to talk about most of the time today, then this pattern here that explains the data is a partition of the data into separate clusters. Right? Okay. So the solution we are looking for is not an individual pattern, but a distribution over these patterns, namely the posterior distribution. So we start with a prior guess on how these patterns are distributed. We add in what the data looks like. And then we compute the conditional distribution of the parameter given the data, or of this pattern given the data, and say, okay, this pattern is more probable and this one is less probable. Yeah, that is the solution that we would ideally like to have. Okay. And now I have to say a few words about exchangeability. I'm going to get back to this tomorrow, but it will already come up several times today. And so the question we ask here is, we're making this assumption that the data is, in some sense, pattern plus noise. And this is really crucial to what we're doing for several different reasons. One reason is that if this noise part here, if this is correlated, then it's really hard to do inference. Yeah, it's really hard to estimate what the pattern is. But there is another, like, a bit more fundamental reason, basically, which is what we really want to do here is we say there is something that the data points have in common, and then there is something that is just randomness, and we would like to extract the common part because that is useful information, right? And then we would like to throw away the rest, and that's exactly this assumption here. This is what the data points share, and this is the rest that we would like to throw away. Okay? So what we have to ask is, in which case is this assumption here justifiable? And it turns out that there is a very sharp precise sharp characterization of when we can justify this assumption. Yeah? In Bayes' theorem, which you have seen in Zubin's lecture earlier, this is encoded in the Bayes equation in this factorial here. Yeah? So this here is the Bayes equation. Here is the prior distribution, the parameter. Then up here, the P of xj given theta is the likelihood of data point number j given the parameter. This here is the evidence term, and then we have the posterior distribution of the parameter given the data. Yeah. And you can see that here the likelihood over all data points is a product. And this product says a product over distributions always expresses independence, right? So these data points are independent of each other, but given the parameter value. Yeah? And this is called conditional independence. So conditional independence in general in probability simply means we have a bunch of random variables. In this case, the random variable is x. And they are conditionally independent given theta if they are independent provided that we know the value of theta. And the intuition behind that is these random variables contain information about each other, but all of that information is summarized in theta. So if we know theta, then knowing some of the random variables won't tell us anything about the others. Okay? That is conditional independence. So this here is a conditional independence assumption, and that is exactly what we have here. We basically, so we can rephrase this question and ask, under what conditions can we make such a conditional independence assumption for data? And if we look back at the picture on the first slide, but then we also see this conditional independence assumption in there, which is in this case, the red line is a theta, right? And then the data points scatter around that independently. So if we know the location of the red line, then no data point will tell us anything about where the other data points are. If we don't know the location of the red line, and we know part of these data points, now where's the next data point going to be? We can tell that it's much more likely to be in this region than somewhere over here. Yeah? So unconditionally, they're not independent. Okay. So now the definition that we need, or the characterization that we need in order to give a criterion for this conditional independence is something called exchangeability. And exchangeability is the following. We assume that we see an infinite sequence of random variables. Yeah, that's data. So that is an infinite sequence of such blue dots here, for example. And now we we look at the joint distribution of this data. And now we ask, what happens if we permute the order in which these data points come in? And the distribution is called exchangeable, or also the sequence is called exchangeable, if the probability of seeing a particular sequence of data points does not depend on this order. So we can permute them, and it will not change the probability of occurrence. Yeah? So very simply, the order of the observations does not matter. And this is a very nice, it's a very nice assumption for several reasons. One is it's certainly true if the data is IID, right? See, if the data is IID, we can shuffle it around. And so but it doesn't have to be IID. And so it's a more, in a sense, it's a more it contains the assumption that we usually make in parametrics, or in non-parametric statistics, the IID assumption as a special case. Okay, so that's a good start. In a way, it's actually the same thing as the IID assumption, but let's not get into that discussion. Another thing is that one thing is it's often true, yeah. The other thing is it's also relatively easy to argue whether this is true or not. Yeah, if you know something about how your data is being generated, then it might be very hard to argue that the data is IID. But it's reasonably easy to say, okay, the order in which the data come in contains information or it does not. Yeah, just if you know the generative concept. Okay, so this is exchangeability. And now there is this the theorem called Definetti's theorem, which is really one of the very basic theorems underlying Bayesian inference. And this tells us, in short, it tells us the data is conditionally IID if it's exchangeable, if and only if. Yeah? So we can check whether this conditional IID assumption, whether that makes sense, by checking whether the order in which the data points come in matters or not. And let's look at this in a bit more detail. So what we see over here is again the joint distribution of the data points. And what we have here on the other side is an integral over the parameter, and I've now written the parameter here as a probability distribution. Yeah? The parameter is now a probability distribution. And this here is again the prior distribution, and now the prior distribution is a distribution over probability distributions. Okay? So we sample a random probability distribution from this cube, then we fix it, and we sample these points from that distribution that we have just generated at random. And how do we sample them? IID, because we have this product here. Yeah, the product says it's IID. Okay, so what this here says is a distribution is exchangeable if and only if we can generate it in this way. Yeah, we put a sum distribution on probability distributions. We draw from that, we draw a probability distribution at random, fix it, and then sample data from it, IID. Okay. And this here is exactly, if you will, this is exactly the term that we have seen here in the base equation. Takes a prior, sample a parameter from it, and then we get a product over the data from it. Okay. Okay, so what this theorem says is, if and only if the data is exchangeable, this whole idea, data is pattern plus noise, makes sense. And the pattern, in general, is expressed by a probability distribution. And if we do something like saying on the previous slide here, oh, our pattern is really a straight line, this is not a probability distribution, then that would mean that we choose a set of probability distributions that are parameterized by straight lines. Okay? Good. But the caveat here is, what this does not mean is you start with some Bayesian model where your likelihood is, say, a Gaussian. And now you say, okay, my data is exchangeable, and therefore this assumption makes sense. Because in general, this here, this probability distribution here is an arbitrary probability distribution. And that means the set in which these probability distributions live is if you want to really exploit the statement of this theorem, if you want to really use that, then you have to be non-parametric. Okay, you have to use infinite dimensional parameters. Okay. Good. So now clustering. Zubin has already mentioned clustering earlier. Basically, the very simple thing. This is just a cartoon picture of clustering. Yeah. So this data was, of course, generated by sampling from a Gaussian mixture model. Is anybody? Yeah. Can I just ask who has not seen a finite mixture model before? Okay. Very good. Thank you. So we're going to assume that we have observations x1, x2, and so on. And the modeling assumption we make in clustering is the data is subdivided into groups, partitioned into groups, and that means each data point belongs to exactly one cluster. Yeah? And in this case, the unknown pattern that I was talking of before, so or theta, if you will, the unknown pattern is the partition of the data into disjoint groups. Yeah? And if you now think of if you think of this as an infinite sequence here, then it has indices 1, 2, 3, 4, and so on. And we can partition it by partitioning the indices. Yeah? So what we are looking for in that case is a partition of n, or if we only see a finite number of data points, 1 through n, then we look at it for a partition of this finite set. Yeah? And here on the side, I have a very simple application of clustering. So what I did here is I just took a very simple image. It's basically a night sky with some trees down here. Yeah, so we see a sky, a moon, and some trees. And now we want to segment this image using clustering. And the way this is being done here is we take a small sliding window, pass it over the image. Yeah, we slide it over the image. And at each location where the window is positioned, we extract the pixel values within that window and write them into a histogram. Yeah? So we get a histogram associated with each location in the window of the window, and that gives us a mapping from this image into a set of histograms, into a space of vectors of histograms, basically. And then we're going to apply clustering on this histogram space. Yeah. And so we get clusters. The histograms get sorted into clusters, and then what I have done here is I've taken the first cluster of histograms and colored each location where one of these histograms was positioned in blue, right? And then the other one in green and in red. So that induces basically clusters in feature space correspond to segments in the image. That's a very simple application of a clustering method. And what we see here is, so Zubin talked about number of clusters earlier and about model selection. In this case here we have 3 clusters and here we have 2 clusters. Now image segmentation is an ill-posed problem, and actually if you let people segment images, then they totally disagree on how many segments there usually should be in an image. I think in this case here, pretty much everybody would agree that it should probably be 3 segments, or that at least the moon shouldn't be lugged in with the trees. So this is probably not as good a solution as this one. No. Okay, so the way we're going to think about clustering is in terms of mixture models. And a mixture model in general looks like this. So this here is our distribution, the distribution given by the mixture model. Yeah, so this is a distribution of data given some m. Okay, the m is something called the mixing measure. So this is our mixing distribution. Yeah, so this is a measure against which we integrate some component. Think of this, for example, as a Gaussian distribution. The p of x given theta is a Gaussian distribution with parameter theta. And then we have a distribution over thetas here. And there's various things that you can do with it. For example, if you set this here to a gamma, and theta is a scale parameter of the Gaussian, then you get a student distribution. Yeah? But the way we are going to use this in clustering is we're always going to look at a specific form of mixture, where this here is a distribution of finitely many or sometimes infinitely many delta spikes. Okay? And what mixture models in general always express, and what I think everybody should always keep in mind when they look at mixtures, is they express 2-stage sampling. Yeah? So what this mixture model expresses is we sample x from this model here by first sampling theta from this distribution. Then we plug it into this distribution and sample x from that. Okay? So mixture models are two-stage sampling. And now a finite mixture model in this formulation looks like this. That is, again, simply a mixture model, but we have a specific form of this mixing measure, and that is it's the sum over delta spikes at k possible locations. Yeah? So this is a finite number k here. We have k different values theta on some parameter space, and we place a delta spike at each of them, and then we weight them with convex coefficients. This is a convex combination of delta spikes. Convex combination means these c values here are non-negative and they sum to 1. Okay? So that means this is a probability distribution, and we when we sample from this distribution, the possible values that we can get are these thetas, and they occur with probability. So theta k occurs with probability ck. Okay? So this is a finite mixture model. Now we can be Bayesian about this and introduce something called a Bayesian mixture model. And the way we do this is, the idea is very simple. If we look back here and we see we define a finite mixture model in this way, what do we have to choose? Well, we have to choose this component distribution here, and we say, okay, let's say a Gaussian, okay, for a Gaussian mixture model. And now we have parameters, and the parameters are the mixing coefficients and the locations or the parameter values of the individual Gaussian components. Yeah? And that means all the parameters of this model are summarized in this mixing distribution. Okay? The mixture model is parameterized by the mixing distribution. So what we have to do is we have to generate the mixing distribution at random if we want to be Bayesian. The parameter is the mixing distribution, we have to do a prior on that. And so the object we want to get is something like this, and now I have capitalized the c's and the thetas because they are now random variables. Okay? We want to generate that at random, and similarly I have capitalized the m. We want to generate a random mixing measure. And the idea in the Bayesian mixture model, so the Bayesian mixture model is something that was introduced in the literature in the 1990s, and specifically the idea there is use the conjugate prior on each parameter. So Zubin has mentioned conjugate priors earlier. Let's just quickly repeat the definition. So a Bayesian model, we call a Bayesian model conjugate if the posterior distribution is an element of the same class of distributions as the prior. Yeah? And this is also called closure on the sampling, because you start with a prior, then you sample data and you condition on that data, and you remain within the same class of distributions. Yeah? So the class of distribution is closed under this process. And there are these pairs of, so conjugate priors occur, except for some pathological borderline cases, they occur only in exponential families in the parametric case. Yeah? So if you slam on some regularity conditions, they only occur in exponential families. And in an exponential, the kind of generic formula of an exponential family looks like this, right? I suppose you've all seen that before. This here is a sufficient statistic, parameter, normalizing constant, and a modulator. And from that you can generically produce a conjugate prior with this formula. Okay? So there's a generic conjugate prior corresponding to each exponential family distribution. And some prominent pairs are the Gaussian, then you have a Gauss-Wishart prior, so a Gaussian on the mean parameter, a Wishart on the, or inverse Wishart on the covariance matrix. You have a multinomial. If your likelihood is multinomial, then the conjugate prior is a Dirichlet. Okay? So what we're now going to do is we're going to assume that we're going to require that all the mixture components are exponential families, so Gaussian or some other exponential families, and then we put the respective conjugate prior on each parameter, and that is called a Bayesian mixture model. And that accounts for the thetas, but there's still the c's. And the way we deal with the c's is we notice that if we sample from this model, then the index of the cluster is distributed multinomially with this vector as a parameter. That is simply due to the definition of the mixture model, right? The index of the cluster we get is multinomial distributed, and the parameter of the multinomial distribution is this vector of coefficients. And the conjugate prior of a multinomial distribution is a Dirichlet. So we're going to use a Dirichlet distribution on this number of on this weight vector here. Okay. So in summary, Bayesian mixture model it's a finite mixture model. We use exponential family components. We use a natural conjugate prior, respective natural conjugate prior on the thetas, and the weight vector is distributed according to a Dirichlet distribution. Okay. All right, and so what that gives us is a way that what this prior generates, this bunch of conjugate priors together, we sample from them, what they generate is a random quantity of this form, right? Okay, and now we're going to do this in a non-parametric way, and we're going to be non-parametric by making the number of clusters infinite, right? So here the number of parameters is fixed and finite because we have a fixed k. If we make this k infinite, then we get an infinite number of parameters, and that's a non-parametric model. So we have, in a non-parametric way, in a non-parametric model, we have to generate a quantity like this here at random. Yeah? We have to think about how we can do that. And again, our restriction is that this now infinite sum over C's has to sum to 1. And the simplest distribution that we can, in a sense, that we can come up with that does this is the Dirichlet process. Yeah? And then there's a range of other distributions which also do that. But if we just think about what is the simplest possible way that we can come up with a distribution on an object like this, yeah, what could we do? So first of all, what does simple mean? Simple means in particular, so simple means that we have as much independence as possible. If these random variables, these C's and thetas, if they are highly dependent, then it will be absolutely impossible to do inference in that model. Okay? So it's certainly helpful for us if they are independent. Okay. And so how can we generate something like this and make these random variables as independent as possible? Well, these locations of the atoms, we can certainly just start with some distribution and sample independently from that. And that's exactly what we're doing in the Dirichlet process. So we start with some distribution that we call G0. That is a distribution on the space of these thetas. And we sample IID from this distribution, an infinite sequence of thetas. Now what about the weights? We cannot possibly make these weights independent. They cannot be totally independent because they have to satisfy this constraint here. And that cannot be independent, right? If we draw the first weight and we know its value is 0.5, then we know that none of the other weights can have a value larger than 0.5 because they have to sum to 1. So we know something about the remaining weights. They couple through the normalization constraint. Okay? But what is the next best thing that we can do to being independent? The next best thing that we can do is we can instead sample independent proportions and use them to generate these weights. And the way you do that is you start with the total amount of mass that you can distribute over these weights, which is just the interval 0, 1. Yeah? Think of that as a kind of budget. And now we're going to sample a proportion, which is a random variable on 0, 1. And say the first proportion is 0.3. And then we're going to use the current budget and take 0.3 of that current budget. So in the first step, that's simply 0.3. What remains is 0.7. Okay. Now we sample the second proportion. If that is 1/2, then we take 1/2 of the remaining budget. The remaining budget is 0.7. We take 0.35, and so on. So basically, each time we sample a proportion and we cut off this bit and use it as our weight. Yeah. And that means that step by step we eat up this budget and it converges, this process converges to 0, right? And that means that these weights converge to 1, this weight sequence. And the way we sample these proportions, well, we have to put a probability distribution on values between 0 and 1, and the simplest distribution we have on the interval, on the unit interval, is a beta distribution. And if we set the parameters of the beta distributions to 1 and alpha, then this whole model is the Dirichlet process. And we see that we have made two choices here. We have to choose the alpha, and we have to choose the distribution that we put on the thetas. And so these parameterize the Dirichlet process distribution. Yeah? And we call that a Dirichlet process alpha G0. Yeah? This is a bit funny, this notation here, but it's a standard notation in the literature, so I just stick to it. Okay. So, and when you want to write that out as a formula, you get something like this. So the weight CK is generated by this product here, and what you see here is the big product term here, which ranges to k minus 1. This is exactly this process where we we cut off a bit of the budget. Yeah. So this is what we have done so far, and this term here describes the budget that is left. Yeah. And now VK is the current proportion, and we take that out of the budget, and that's CK. Yeah. It's very simple. So we want to generate an object for this, and if we do that in a way that is basically as maximally independent as we can get under the constraints, then what we get is the Dirichlet process. Okay. I think I should probably take a short break. 5 minutes. Is that a good idea? Yeah. Coffee?
So this way we can automatically divide into two. This is the code that I'm going to go over in the afternoon session. If the connection is too slow and you cannot download it, please don't just keep trying. Let the others download and share with each other using USB sticks. Okay? Huh? I'm not sure how big. I don't think it's very big. Still, the connection will be
There's actually a good algorithm, it's called the Aloha network. If you try and download it, doesn't work. Sample a gamma, an exponentially distributed random number from MATLAB, and that's the number of minutes you should wait before you try and download again. And that's called the Aloha network, and it will prevent collisions.
12.
It's
And when are we supposed to end?
1:30.
1:30, okay.
YWTEK, sorry, TEH, I can finish with it. Teaching anti-bias. Look for EY test.
Is that solution a Nash equilibrium?
All right, I think I should probably continue. It's, yeah, I know this takes time to digest, but can we start again?
Yeah.
Okay. Right. So, okay. So what we have just seen is one way to construct the Dirichlet process. It's not the original way that it was constructed, but it's by far, I think, the simplest construction. And this is also known as a stick breaking construction. That is probably something that a term that most of you have heard before. Yeah? And the idea is that you imagine this this budget of 0, 1 as a stick, and you break off parts. That's why we call it stick breaking. Yeah? Okay. So. What we did before was we put a prior distribution on an object like this here with a finite number of clusters. Okay? And now we see that we have a way here of generating an object like this with an infinite number of these delta spikes. So we could at least try to take our Bayesian mixture model, take out the distribution on the finite sum of delta spikes, and put in this distribution, this Dirichlet process, instead as a prior. And then we could do clustering with an infinite number of clusters. Of course, that is only going to work if we can compute posteriors and if we can do inference in that model, right? And I mean, at first glance, it's not clear how that should be possible with an infinite number of clusters. So now it turns out that the Dirichlet process has a particularly nice and simple posterior distribution. And the way it looks is, it looks like this. So we are observing, we assume that we have observed n draws theta from this distribution. Yeah? And I mean, we're sampling here, but I'm writing theta and not x because these are parameter values and not observations. So, but assume for the moment that we actually observe these thetas here. Yeah? And then we can condition on them what is the posterior distribution of our process. And it looks like this. So it's a sum over all the locations that we have seen so far. Yeah, so these are the delta spikes at these locations. And then we interpolate that with a weight here with the probability distribution that we use to sample the thetas from. Okay? So now that on the previous slide we were sampling IID from this distribution. But now we have already seen n samples from that, and we condition on that. Then the next sample is distributed according to this formula. And what does it say? Well, it says that with a certain probability, which is proportional to the number of data points that we have already seen, we're going to draw from this term. Yeah? And then with a probability proportional to alpha, we're going to draw from this term. If we draw from this term, what is going to happen? We're going to see something again that we have already seen before, because the distribution is made up by these delta spikes, from these delta spikes. Yeah? We're going to pick one of the points that we have seen before. And that means that points reoccur as we sample. Yeah? There is a probability alpha that we're going to draw a point from this term. And if this distribution here is smooth, if this is say this is a Gaussian here on Euclidean space. Yeah? From a Gaussian, we're never going to draw the same point twice. That's a probability zero event because it's a smooth distribution. And so if we sample from this term here, then we're going to see a new point with probability 1. Yeah? Whereas when we sample from this term here, we get a point we have already seen with probability 1. Okay? Now, how likely are we? So points are reoccurring, and that means we actually get clusters, right? We have something here that is called a clustering property or a rich get richer property, because with a certain probability we're going to see a point again, and then you can see here that if in these endpoints here we have seen a certain location already 10 times, say, then the probability when we sample from this term again that we will see this particular point is proportional to this 10 times, or to the number of times we have already seen it, right? Because we're summing evenly here over all points. And that means that if we interpret these locations here as clusters, then as we see more and more data, sampling from a cluster that is already large is more probable than sampling from one that is small. Okay? So basically this term here is, we're sampling from it. This here is essentially represents a finite mixture model. And this term here represents creating new clusters. Okay? And we can tune the probability with which we are creating new clusters by adjusting this parameter alpha. Okay, now if we use this in a mixture model, then we have to take our distribution P, which is a mixture component, our Gaussian or our multinomial or whatever we're using as a mixture component, and we have to integrate it against this term here, right? Let's quickly go back to the mixture. We have to compute this integral. The M is now something that we draw at random from the Dirichlet process. And we have to integrate the P against that. What is going to happen if we do that? Well, if we integrate something against the delta spike, then it simply picks out the function value at that point, and we're integrating over the theta variable, over the parameter variable, and that means we get a parametric model, if this here is a parametric model, with a fixed parameter value. Okay. And you can see that I have added a little star here to this parameter value, which is also customary in the literature again. And that is to say this is one of the points that we have already seen. So this is one of our cluster parameter values. Okay, and then we get a second term over here, and we can't simplify this integral in general. Yeah? This integral, this here is also an integral, but it simplifies. This here does not simplify in general. If we have a conjugate relation between those two, so if we choose this here as an exponential family model, and this here as its natural conjugate prime, then this integral here simplifies, and we can express this in terms of the conjugate posterior. Yeah?
Shouldn't theta k star something to be integrated out? In the left, there's no theta. If you look at the left side of the equation, it is not a function of theta.
This here. Yeah, that's right. So that's true. So this is a bit. In this case here, when we're using this in a mixture model, we're not actually observing the thetas. Yeah. Okay. So the thetas are latent variables, and that is also something we have to take into account when we do inference. And that is just like in, say, in a finite mixture model in an EM algorithm, where you also don't observe the cluster parameters. You only observe the data points. And then you're trying to guess back what the cluster parameters have been that account for these data points. And that's exactly what we're going to do here. But basically, because all we know is what the previous data points look like, if not written in the thetas here. Okay. All right. So this is one way in which conjugacy very often occurs in the context of Dirichlet processes. That is, we usually want to choose this here as an exponential family and its conjugate prior to make sure that we can compute this integral. And if we don't do that, then we have to come up with something else, like numerical integration, for example. Yeah, which is not impossible, but it might be a bit of a pain. there's another form of conjugacy here, and that is the following. So if you remember the way I defined conjugacy before, it's the distribution. A Bayesian model is conjugate if the posterior distribution is in the same class of models as the prior distribution. If you look at this here, then you see that this here is actually a Dirichlet process. Okay, and the Dirichlet process in particular, or I don't expect you to look at this and say, oh, that's a Dirichlet process. I'm telling you, this is a Dirichlet process. Okay, so this is a Dirichlet process distribution, and its parameters have changed. Yeah, so we looked at the prior, which was a Dirichlet process with parameters alpha and G naught. Yeah, and the parameters of this distribution here are alpha plus n, the number of data points. Yeah, so the probability of let me get to that in a second. And the probability of the thetas is now changed to this term here. Yeah, so we're now it's not just the G naught anymore, but we're interpolating the G naught and the points that we have already seen. Okay, and what this means is, according to the definition of conjugacy, that the Dirichlet process itself is conjugate. Okay, so this here, if we make these conjugate, this is conjugacy on a finite dimensional parameter space for this parametric model that we're using as a cluster component. Yeah, this here is conjugacy on the infinite dimensional space. So the Dirichlet process itself as a model is conjugate, and we're going to get back to that tomorrow. Actually, yeah. The previous one, this one.
No, I was wondering. It seems to me that this type of construction could be quite sensitive to initialization. Right?
Which construction? This here?
Right.
Yeah. Okay. So the question is this kind of construction sensitive to initialization? I think an exhaustive answer to that would take several hours, and it's actually really interesting. But so basically, no, it's not a big problem, and the reason for that is that this model is exchangeable. Yeah. So the order in which the data points come in does not change the distribution. Okay. And this actually, the way in which these weights are set, you can see here that as we see more and more data points, as n gets larger, the probability of creating a new cluster becomes smaller, right? Because it gets divided by n plus alpha. So this weight here becomes smaller as n gets larger. And that is actually a necessity in order for this to be exchangeable. Okay? But you're totally right, because obviously these data points are not independent of each other, right? Because it depends. What we're going to see here, which clusters we're going to see later on, depends on what we sample first. And in a way, the clusters that, or the points that we observe early on play a bigger role than points that we observe later. Okay? And these kind of models are described in probability theory by something called an urn, or a Poya-type urn. And probability theorists can get totally high on these models because they have the property that they have random limits, which is something which is exactly due to this point, and it's something that is very rare in probability theory. In a way, the whole cornerstone, or one of the cornerstones of probability theory is, for example, in the central limit theorem, if you take a large sum of independent random variables, then as you add more and more components to the sum, it becomes less and less random. Yeah? That is a phenomenon called concentration that Gabo Lugosi is going to talk about later this week. So, in a way, if you aggregate lots of random events and they are reasonably independent, then the randomness slowly fades out, and in the limit it becomes something deterministic. And that is a very important, one of the reasons why we can handle probabilities. On the other hand, it also makes it very hard to produce aggregation effects or aggregation processes where the limit is still random. Yeah? And these urns have this property, and it's exactly because the terms early on in the sum play a bigger role than those further on. Yeah. Okay. Good. So just keep in mind the Dirichlet process is conjugate. And keep in mind that there's two forms of conjugacy here. One is the Dirichlet process and its posterior conjugate. And one is we want to use a conjugate parametric model in here to be able to solve this integral. Yeah. Okay, so how do we do inference in these models? Yeah, I don't want to talk much about inference, but I think these models are, you know, we're talking about a model here with infinitely many clusters, and I have to tell you a little bit about how we can possibly even think about doing inference in that. But it turns out it's actually surprisingly easy. Okay. So I've just written down the mixture posterior here again. Oh yeah, and one thing I should remark. So you see that I've changed the notation slightly from here to here, and what I have done is I have collected these terms into clusters. Yeah? We have seen that if we draw more and more points, these points keep reoccurring. And basically what I've done here is I've said, okay, I just count how many times each of these theta j's reoccurs and then collect them together. And that's why here I have a sum over the number of data points, and here I have a sum over the number of clusters. Yeah? So capital Kn is the number of clusters after I have seen n data points. And this is a random variable, right? This is a random variable. And this nk here is the size of cluster number k. And actually I should probably have also written this as a capital letter because this is also a random variable. Yeah? This n here is deterministic, but this n here is a random variable. Okay, and here I just have reproduced the formula from the previous slide that so you can look at it. Okay, so in this formula, as I just mentioned before, the thetas are not actually observed, right? We assume that what happens is we draw this random measure from the Dirichlet process, then we put it into our mixture, and then we sample from the mixture. And what we see is the data from this mixture, and now we would like to guess back at what this mixing distribution has looked like. And the way we do that is with an algorithm, with a Gibbs sampling algorithm that I think is the easiest way to understand this algorithm is to think of it as a kind of EM algorithm, because that is really what it is. It's kind of a sampling version of EM with an infinite number of components in the mixture. The way it works is the following. We compute a matrix of assignment probabilities for the data points that we have seen. Yeah? So we have seen data points 1 through n. The rows correspond to data points. And the columns here correspond to the clusters, to our current estimate of what the number of clusters is. Yeah? So this is not necessarily the true number of clusters, this is the estimate that our algorithm currently thinks is a number of clusters. And those are these rows here. And then we have an additional row over here, and that corresponds to the probability of creating a new cluster. Okay? So basically we take these probabilities here correspond to the kn terms in this sum. And these probabilities over here correspond to this integral. Yeah? So we get this from evaluating this term. We get this here from evaluating this term. Then we write them all into a matrix. And then, because they should be assignment probabilities, we have to normalize them by rows. Yeah? So each row adds up to 1. Okay? And this is exactly like the matrix of assignment probabilities that you compute in the E step of an EM algorithm, except for this additional row, for this additional column here. In the EM algorithm, we don't have a device for creating new clusters in a finite mixture model, so we don't get this probability here. But basically, if we would just cut this out, take this partial matrix here and renormalize each row to 1, then we would have exactly the assignment probability matrix in the EM algorithm. Okay, and now how do we do Gibbs sampling with this? Well, we use this matrix here to sample assignment variables. Yeah? So these are variables which the value of this variable is a cluster index. So for each observation xj, we have a variable phi j, and the value it takes is the index of a cluster. Yeah? So 1 through kn. Or it could take value 0, and that means create a new cluster for this point. And how do we get this variable? Well, we take the corresponding row, the row corresponding to xj, and we sample multinomially from that. Yeah? So basically what we're saying is we assume that these terms are currently our mixture weights, or our current estimate of these weights. We sample multinomially from that. Okay. We do that for each point sequentially because it's a Gibbs sampler. And then we get, for each point we get a cluster assignment. And why is it important that we do that sequentially? Because if we at some point, if we draw an assignment to this term, then we have to create a new cluster. The number of clusters become larger, and then we have to recompute this matrix, and the next term could be assigned to that cluster, right? So what happens at some point as we go through this matrix, what happens at some point in this iteration can influence further points, and that's a characteristic of a gift sample. Okay, so that is the assignment step. We sample this variable here multinomially, and then we have this really corresponds to the E step in the EM algorithm. And then we have another step which is corresponding to the M step in the EM algorithm where we sample a parameter, and what we do here is we take all the data points that are currently assigned to a given cluster, and then we compute the posterior distribution of the parameter for this cluster and the posterior distribution of the component, right? So what we have here is the parametric component in the model is this P here, right? Then we have usually a conjugate prior on that, on the theta. And we compute a posterior under that and sample from this posterior. But we only take into account the data points which are currently assigned to that cluster. Yeah? Now, if you compare that to an EM algorithm, what are we actually doing differently? First, of course, this row here, we can add extra components. Yeah? Another thing we do differently is in an EM algorithm, we just use this matrix and compute weighted maximum likelihood estimators. So we don't actually turn this into assignment to a single cluster, but we use weighted assignments to different clusters. Yeah? The point has assignment probability, it's not assignment to a single cluster. So we turn this into a hard assignment here, much like the k-means algorithm does. Yeah? We use hard assignments. And then another thing is that in an EM algorithm, this here is not sampled, this is computed by maximization. Yeah? But what we do here is instead of maximizing, we sample. And again, here in the parameter sampling step, we also sample a parameter value rather than maximizing it. Yeah. So basically, that of course usually means that points that are close to the mode of the posterior, to the peak of the posterior, are more probable to occur than points that are further out if it's unimodal. Yeah. And the mode is exactly what we would get if we would do a map EN here. Yeah. So basically, this really looks like a sampling version of the EM algorithm with this extra row here. And another interesting thing is if you really use this algorithm here, this gift sampler, but you don't use this extra row here for creating a number of clusters, for creating a new cluster, then you have a gift sampler for the Bayesian mixture model. Yeah? And actually, at the time in the mid-90s when this Bayesian mixture model was developed, these two communities, independently of each other, came up with the first gift samplers for the Dirichlet process mixture, and with gift samplers for the Bayesian mixture at about the same time, independently of each other, and they were essentially the new algorithm, the same algorithm except for this row here. Yeah. Okay. So, yeah. So I think what you should keep in mind is this works kind of like an EM algorithm, and the reason why we have to use a latent variable algorithm is because we don't know the cluster assignments. The cluster assignments are hidden, they're late, right? We don't observe that. Okay. So, now, I said earlier that basically in order to use such a non-parametric mixture model, we have to come up with some way to define a prior distribution from which we can generate this this infinite weighted sum of Diracs, right? This random mixing measure. So, and the Dirichlet process is simply the easiest way of doing that. And you can think about whether it would do us any good to come up with more complicated ways. Is it interesting to look at other models? If we can, we have one way of doing infinite mixtures. Is it interesting to look at other models? So, when we look at the properties of the Dirichlet process, one thing that we can look is how many clusters do we expect to see when we sample from a Dirichlet process, right? And there's one of the old questions in clustering, whether Bayesian or non-Bayesian, is how many clusters? What is the right number of clusters in a data set? Yeah. And what the Dirichlet process gives us is an estimate of the number of clusters, and we can ask how good is that estimate. Right. Okay, so the number of clusters, you can show in that in a Dirichlet process, the expected number of clusters that we see in n samples grows logarithmically with the number of data points. Yeah? And the logarithmic growth is due to the fact that here is a picture of that where we simply sample from a Dirichlet process. Each blue dot here is a sample, and down here we see the number of observations increasing, yeah, the number of points that we have sampled, and then here we see what cluster they are assigned to. So these are the clusters in order of occurrence. Yeah. So the lower a cluster is here, the earlier it has occurred in the sampling process, and this envelope here, yeah, this kind of it's not traced out as a line here, but you can imagine that you have an envelope function. Yeah, this is like this corresponds to the creation of new clusters. Okay. All right, and you can see that this develops in a roughly logarithmic sense. Yeah, roughly logarithmic. Okay, and you can also see here where this comes from. If you look back at this formula here, you can see we already noted that this probability here of creating a new cluster decays as the number of data points gets larger. Right? So, and that is because that is reflected here in the fact that as we see more and more data points, this curve starts to even out. Yeah. Okay. So that means we have a modeling assumption in here, and a modeling assumption on how many clusters we expect to see. Yeah. But there's a very basic thing that you should note here, and the difference between using a model like this and using a finite mixture model. Whether it's a Bayesian mixture model or a simple finite mixture model doesn't matter. But the difference between these models and finite mixture models is in a parametric clustering or in a finite mixture model, the number of clusters that we see in an infinitely large data set, yeah, so when we let n here go to infinity, the number of clusters in an infinitely large data set in the underlying population is assumed to be finite. Yeah? Whereas in a these non-parametric clustering models, Dirichlet processes and all others that we're going to see, the assumption is always that the number of clusters is infinite. Of course, in n data points, we're going to see at most n of these clusters, but the assumption is in the underlying data, the number of clusters is infinite. And usually that's actually a good assumption, but you really have to think about it, right? So I showed you this image segmentation example in the beginning. If you imagine, for example, that you have that the entire data set is an astronomically large image, and now you see only a tiny fraction of that image. Okay, so the picture that we saw earlier would be a tiny little fraction of a huge image, and then in that image we only see a finite number of clusters, of course, or of segments. But now, if we make the image larger and larger and see more and more of the world, do we expect that we also always see more segments at some point? Or do we assume that there is just a finite number of segments in the world that we can possibly see, right? That is the kind of question you have to ask. And in some cases it makes perfect sense that the number of clusters should be finite, and then you should not use one of these models as a device to estimate that number of clusters. Yeah? You would have to do something else. You would have to, for example, use a Bayesian mixture model and put a prior of the number of clusters. That would be the right way to do it. Yeah? These models always have the assumption that the underlying number of clusters is unbounded. Okay. And the number of clusters, so this question for what is the right number of clusters can now be rephrased when we look at this here. Yeah, we can rephrase it, and we're actually asking for something that is that contains more information than just the number of clusters, because we're not asking what is the right number of clusters. We're asking what is the right distribution on the sizes of these clusters, and the number of clusters is an outcome of that. Yeah. Okay. So what we have to ask is what should we assume about the distribution of the cluster sizes, and there's one generalization of the Dirichlet process, which is of course not as popular as the Dirichlet process, but it's I would say in second place, and that comes comes exactly, so that addresses exactly this kind of question. So what I've done here is I have written out, again, the distribution, the posterior distribution for the Dirichlet process mixture. And now I have changed it a little bit, yeah? And the result is something that is called the Pittman-Yaw process, which is a generalization of the Dirichlet process. It contains the Dirichlet process as a special case. And I have marked the things that I have changed in red. So the black part is precisely, excuse me, the black part here is precisely the Dirichlet process mixture. And then we add a parameter, a new parameter d here. And this parameter takes values between 0 and 1. Okay? And I subtract this parameter here from the cluster size in this term corresponding to the clusters that we have already seen. And then in order to correct for that, because these weights overall have to sum to 1, I have to add it again here. And since I have subtracted it once for each cluster, I have to multiply that with the number of clusters. Yeah? That's the only thing that I change. It turns out that this very innocent looking change makes the model a lot more interesting, also from a probabilistic point of view. Yeah? This model is actually a big deal in probability theory these days. Okay, and what is going to happen? So if this parameter is between 0 and 1, we can look at the two extreme cases, right? The first thing we could do is we could set this parameter value to 0, and then nothing happens here, right? So we're back to the black case, and that's exactly the Dirichlet process. So for 0, we recover the Dirichlet process. The other case would be that we set it to 1. And if we set it to 1, what is going to happen? Well, the first time we sample from a cluster, this cluster size here is 1. Okay? And that determines the probability of sampling from it again. Now, if I subtract 1 from that, this coefficient becomes 0. And that means we're never going to sample from that cluster again. And what we're going to end up with is one cluster for each data point. Okay? And if we look back at this slide here, so in the one extreme, where the number of data points, in one extreme we have the Dirichlet process, and the number of data points is going to grow logarithmically with the number of clusters is going to grow logarithmically with the number of data points. In the other extreme, we get one cluster for each data point, and so this growth is linear. Okay? And that means by adjusting this d here between 0 and 1, we can interpolate between a logarithmic and a linear growth in the number of data points of the number of clusters. Yeah? All right. And what we see here is again a sample from the Dirichlet process, and then here is a sample from this Pittman-Yaw process where d is set to 1/2. You can see that the number of clusters increases even as we see more and more data. The number of clusters increases more strongly. Okay. All right, and this relates to something that is called a power law. So the distribution that these kind of distributions that we can produce in that way, the ones that interpolate between logarithmic and linear, are called power laws. And power law because the size of the cluster, or the expected size of a cluster, and of cluster number j, yeah, decreases as j increases. So as we see more and more clusters, we tend to see smaller and smaller clusters. And how does it decrease? In proportion to j to the power of minus some constant between 0 and 1. Yeah, and because of this exponent, because of this power, it's called a power law. Yeah? That's kind of okay. Okay, but these power laws occur in several real-world problems, and that is one reason why this is also a topic that is, one really of the current research topics in probability theory. Yeah, for one reason is that they are theoretically very interesting. They have very interesting properties. They are essentially, I mentioned earlier that probabilists are interested in these ERN models, which generate random limits, and these ERNs also are the processes, the generative processes which create these power laws. Okay? So from a theoretical point of view, people are interested in that, and the other reason is that it's just that they occur in some very important problems in the real world. And one of them is word frequencies, and another one is in social networks, the popularity of people, or the number of friends that people have. So what do these power laws express? What they express is basically that you have small number of clusters which are very large, and then you have a huge number of clusters that are small. Okay? So the distribution the distribution over the number of clusters, if you order them by size, starts very large and then it falls off and it has a heavy tail. And you can easily imagine that that is the case in word frequencies, because there are a few words, like articles, for example, which occur essentially in every sentence. And then there's lots and lots, thousands and thousands of words which are much more specific and which only occur in certain contexts. Yeah? So if you simply count, if you take a very large corpus of language, which is take a library, and count all the words that occur in that library, then you will find a few words that occur in almost every sentence, and then lots and lots of words which occur only rarely. Yeah? And that's a power law. And similarly, in social networks, there are like some people, like celebrities, for example, who have a huge number of friends. I mean, friends in the social network case, right? In the social network sense, and then normal people who have only a small number of friends, right? And there's much more normal people than there are celebrities. Okay, so for these kind of problems, models which can express a power law like this Pittman-Yaw process are simply more adequate than a Dirichlet process. Yeah, and one case where this is used quite a lot is language modeling, and this here is a plot where we see word frequencies modeled by a Dirichlet process. That is the red line here, and it's a log-log plot, so a power law should be roughly linear. Okay. Then we have word frequencies as they actually occur in English text. That is the black line here, this one here. So that is an empirical value. And then we have word frequencies as modeled by a Pittman-Yaw process. That is this blue line, yeah, which is of course it doesn't coincide, but it comes much closer. And you can see that since we can, by choosing this parameter, we can interpolate between the non-power law case and the extreme linear case. That means that if we don't know what this coefficient here is, and we usually don't know that, if we don't know what this coefficient here is, then we can try to learn that from data. Yeah? Because we have a model that is parameterized by a parameter that can fit the power. Yeah? So with these models, we can fit power laws. Okay. Good. Excuse me.
What do the clusters correspond to in the word example? So the sizes are power laws, right? So
Yeah.
What are the clusters like?
The classes are simply words. So here you can simply count this plot here of for English text, right? It's simply counting how often does each word occur. You can, yeah.
What's it to do with solving this to the parameter alpha?
To the parameter alpha. So the parameter alpha, the question is how sensitive is this overall to the alpha parameter? The parameter alpha in the Dirichlet process, also in the Pittman-Yaw process, controls how many clusters we're going to see. And the Dirichlet process is so if you fix the alpha parameter and sample repeatedly from a Dirichlet process, yeah, so several bunches of clusters, you see how many clusters you get each time, then it's a fairly sharp peak that moves as you change alpha. And there are other models. I'm going to mention one model later, which is, it's kind of a recent discovery, but it seems that it is more robust with respect to the alpha. So that would be one interesting aspect of that model. Yeah. So the alpha is important, but it's also fairly easy to estimate. What is a bit harder to estimate is this D parameter here. Because essentially what you're doing when you change the D, then imagine you do that in a sampler, right? You change the D, then you're telling, that calls in question the whole current state of the sampler, if you will, because it says, okay, our estimate, our current estimate of how the clusters are, things are partitioned into clusters is based on the assumption that we have a certain power law here, and now we change that. Yeah? So if you want to estimate the D as well, then you have to expect your sampler to mix slower. Okay. So, yeah?
What is beta and B? Are they same?
No, they are not the same, but they play the same role. Yeah. So you cannot simply plug in the D here for the beta, but there's a one-to-one correspondence between B and D. Okay. So so far I have talked about random discrete measures, right? So this quantity here, this mixing measure, is a probability measure. It's discrete because it is a weighted sum of these delta spikes, and we have made it random. Yeah? So the kind of models we look at are random discrete measures, or random discrete probabilities. And I said earlier that the pattern we are interested in clustering is the partition of the data. Yeah? Now you can see easily that these random discrete measures induce partitions, right? We simply sample from this measure here, and we record for each data point which cluster it belongs to, and that gives us a partition. Right? So partition is the index set of the data. And so more formally, what we do is we say we have a partition of, if we sample an infinite sequence here, then we get a partition of n, which is the index set, into blocks, which I call bk here, yeah, and n is in bk if and only if the nth observation belongs to cluster k. Yeah, very simple. Okay, so that may look like a triviality at first glance, yeah, but it actually, if we look at the distribution of this quantity and the distribution of this partition, then they correspond to each other, but they are slightly different objects. Yeah, and we have to distinguish that. Okay, so whenever we have a random discrete measure, then it induces a random partition. Okay, and the Dirichlet process is a distribution on a random discrete measure like this. So it induces a distribution on random partitions. Okay, and the random. Okay, so one thing I should mention here is, in this case, once again, we have to ask if we have a partition, yeah, if we have a random partition, in which case can we represent it using a random discrete measure? We ask the other way around, right? We know that these random discrete measures induce partitions, but if we have a partition, can we assume that it comes from a random discrete measure? Yeah. And this again, characterizing this brings us back to exchangeability. So just as we call the data points exchangeable if their order doesn't matter, yeah? If we sort these exchangeable data points into a partition, we can call the partition exchangeable if once again we can permute data points between blocks. So if we take the partition into blocks, we take two data points in different blocks and swap them, then that's not going to change the probability. What that means intuitively is that the probability of the partition depends only on the sizes of the blocks. Okay? So in clustering, it would only depend on the cluster sizes, but not on which data point is in which cluster. At that point, you really see the difference between looking at this random measure perspective and looking at the partition perspective. Because if you say, okay, which data point is in which cluster doesn't matter, it sounds very counterintuitive, right? Because data points that are similar should be in the same cluster. But that is because we have thrown away this parameter information here, and we only look at the distribution of the cluster sizes. Yeah? What is the distribution of the cluster sizes? Okay, and you can show in a similar theorem as Definetti's theorem, something called Kingman's theorem, shows that if you have an exchangeable random partition, then it comes from a random discrete measure. Yeah? It's induced by a random discrete measure in this way. If and only if we can. Okay, I'm not going to dwell on this today. I might come back to it tomorrow. But back to these induced random partitions. So we have the Dirichlet process, and it induces a distribution on random partitions. And this distribution on random partitions is called the Chinese restaurant process. So you will probably have heard both terms before. You certainly will if you go to a machine learning conference these days. Yeah, and the connection between the two is The Dirichlet process is a distribution on a random discrete measure, on the mixing measure. The random partition that it induces has a distribution which is called the Chinese restaurant process. Okay? And there's this, you often, in basically any paper that relates to Chinese restaurant processes, you see a picture like this. Yeah? The idea is that these are tables and these are customers. Yeah? And what it very simply means is the customers are observations, and their numbers are the indices of the observation points that come in, and the tables are clusters, so they are the blocks of the partition. Yeah? And then a customer sitting at a table is simply another way of saying the data point is in a cluster or belongs to a certain block. Yeah? I would quickly like to add a historical remark here. So originally this Chinese restaurant process was not introduced as a distribution on partitions, but on random permutations. And Dubitz and Pittman use this, describe something like this, where they insert points on these tables here to generate a random partition, yeah? A random permutation. And this random permutation is infinite. And that is really a remarkable thing, because it was not clear at the time you could do something like this. And they describe this very simple idea with which you can generate this thing. And that is why people in probability theory and more theoretical topics got excited about this. But basically what you do then is, when you generate permutations, the order in which people sit at these tables matters. If you want to generate a partition, the order doesn't matter. It only matters who is in which block, right? So you get the distribution, you get a distribution on partitions by throwing away the order. You forget the order. You have distribution on permutations, you forget the order, you get a distribution on partitions. And that is then also called the Chinese restaurant process. It's in a way a much simpler object, but that is what we always use in clustering. Okay? I would like to make a personal appeal here. If you write papers on some Bayesian nonparametric model, please don't call it Chinese restaurant something. Okay? It's just not funny anymore. Really. It has gone out of hand. It's an industry, don't do it. Don't participate. Build these models, but call them something reasonable. Okay, so when we look at these exchangeable random partitions, these are the objects that we want to use in clustering. Yeah? If we want to do clustering in a nonparametric Bayesian way, then unless something is very odd, what we want to have is an exchangeable random partition as a prior. Yeah? So there are the exchangeable random partition as a parameter. So basically what we have to ask is what distributions are there on exchangeable random partitions. And 10 years ago, basically the only one that we knew, or the only one at least that had already made it into machine learning, was the Dirichlet process. Yeah? And today we have a much better picture of what the landscape of these models looks like, which models are possible, and also to some degree which properties they have, even though there's quite a lot of work still to be done. And I quickly want to tell you a few words about that. Okay. So here's a diagram of certain families of exchangeable random partitions. And we have seen a few of these. So we have seen the Dirichlet process. We have seen the Pittman-York process, and there's an arrow here which indicates that this is a special case of this. Okay, you can obtain the Dirichlet process from the Pittman-York by a certain parameter set. Okay, we have also seen the Bayesian mixture model, where the distribution on the cluster sizes is simply a Dirichlet distribution, a finite Dirichlet distribution. Yeah? So that's parametric, but it is exchangeable. So that is also an exchangeable random partition. And then we can generalize that and take a mixture of finite Dirichlets. So in the prior, we put in a mixture, and it remains exchangeable. Okay, so that is also a way of creating an exchangeable random partition. So basically, the ones I said in blue here are the ones we have seen before, and this one here we're going to see on the next slide. Yeah, and then there's a bunch of others here. So there's this large class of so-called Poisson kingdom models. This has really not been. I think this hasn't really made it into statistics or machine learning. This is so far only studied in probability theory. Then there's something called normalized completely random measures, which is a very large class of models and very useful. But it turns out that in a certain sense, these Gibbs type measures might be more useful. Yeah? But most of this is very current research. So this is all stuff here that was developed over the past 5 years. Okay. All right, and you can see that these Gibbs type measures here basically have arrows to everything down here. Right? So that is a nice generalization. Okay. Let me give you a heuristic description, or a description by circumstantial evidence what these Gibbs type measures are. I'm not actually going to define them, because that would get a bit technical, but I want to tell you what they are, yeah, or how we can think about them. And I will follow this classification here, which has been suggested by Igor Prinster, who's a mathematical statistician. And this is very recent, so he hasn't, he has shown this, he's using it in his talks, but I think the paper is not even out yet. It's just very current research. But I think this classification, since all of this stuff is ongoing work, I can't tell you whether this is the right classification. It might be that in 10 years we just understand things better and we have a better one, but this is, I think, currently our best plausible guess at what things are going to look like. Yeah. And what Igor does here is the following. So he classifies these models according to the probability of creating a new cluster. And that is really a very neat idea because we're interested in the distribution on the cluster sizes, and that is controlled by how we create new clusters, right? So we can look at this probability here and use it to classify these models. And he classifies them according to what this probability depends on. So what could it possibly depend on? It could depend on the number of clusters, right? And if we look back at one of the Dirichlet process formulas somewhere here, so we see that in the Dirichlet process, this is the probability of creating a new cluster, but here we have the mixing distribution. So maybe let's look at the one without the mixing distribution. Here, what does it depend on? Well, it depends on the parameter, but that is fixed when we sample it. Yeah? The only other thing it depends on is the number of clusters. And that is a deterministic quantity. It's not random. Okay? Yeah, so that is the simplest case. And if we only make it dependent on the number of clusters and we demand that the partition is exchangeable, then it is a Dirichlet process. Yeah? The only model which does that is a Dirichlet process. Okay, now let's make it a bit more complicated. We could say that it also depends on the current number of clusters. So that is a big distinction already, because this is now a random variable. Yeah? It depends on one deterministic quantity and on a random variable. If we look back at the Pittman-York process here, then you can see, that is the case here, right? It depends on the number of clusters. Okay? And it turns out that the models, the exchangeable partitions for which this is the case, these are the so-called Gibbs type measures. And this class of models is completely characterized. Yeah? There's a sharp characterization in terms of a formula on these weights of the two terms in the mixture. The term corresponding to the classes we have already seen, and the term corresponding to a new cluster. That an implicit formula which characterizes these measures. And then the third possibility, if we generalize further, is it could depend on, additionally, on the sizes of clusters. So this block n here is the vector consisting of the n k's. So these are the current sizes, or the sizes of the number of clusters that we have, the sizes of the clusters that we have already seen. And the reason to make this distinction here is, so how complicated can these models become, and how complicated do the posterior distributions become? And if you think of that, for example, in terms of sampling, then if this here is fine because it only depends on something deterministic. Okay, here it already becomes a bit more complicated. What I said earlier, that if we change the d parameter in that we can mix slowly with respect to the d parameter in that that relates to this. So if we're depending here, the current state of our sampler will depend on a random variable that is part of the curve estimate. Right? And then here, if we also add in the number of the sizes of the clusters, then it becomes a real mess. Because what that means is that the probability of, if we just take one point in our current solution and change it to another cluster, then that changes our whole opinion on how the sizes of these clusters have come about. Right? Okay, so from that point of view, we can assume that maybe this year is tractable, but this year is probably not. Yeah? And this whole class of distributions that we can assume to be tractable is characterized. Okay, so this gives us these general partition priors here. These measures here, these kind of partitions are were characterized in 2006 in a paper by Canadian and Pittman. And basically, the way what the characterization looks like is, if you look at these two weights here, yeah, then you get, if you abstract these as two coefficients that are indexed by the number of data points and the number of clusters, then they have to satisfy a recursion formula. Yeah, so computer scientists love that, right? Because these kind of two index recursion formulas occur anywhere in algorithmics and data structure. And it's a recursion formula that looks very much like that. So that is an implicit characterization of what these distributions look like. On the other hand, we don't have an explicit enumeration of what they look like yet. So we know a few of these models. Yeah, one of them is the Dirichlet process, of course. One of them is the Pittman-Yaw process, which is in this class here. We know another one which is also in this class. This is something called the normalized inverse Gaussian process. This is the model I mentioned earlier, which is a bit more robust with respect to the alpha parameter. Yeah, and the general theme is what we can hope to happen in the future is that we have a range of these models, and each model expresses a different prior assumption on what the sizes, the distribution of the cluster sizes looks like, which also implies a distribution on the number of clusters. Yeah? And once we have worked out the properties of this, basically what we can give a user is like a lookup table where you can see, okay, if I know this and this and this about my cluster sizes, what I can assume about my cluster sizes, then I should use this prior distribution. So that is really a much richer picture than 10 years ago where we were thinking, okay, Dirichlet process is what we use if we don't know the right number of clusters. Yeah? This is just a very different way of thinking about the problem. Good. So I have about 15 minutes left, and I will use that time to quickly talk about latent feature models. Yeah. So I'm now talking about a model that was invented by Zubin. Okay. And this is called the Indian buffet process.
It's all about food.
It's all about food, yeah. Okay, so this model in my personal view of the history of Bayesian nonparametrics. I think this model is really important because in machine learning it marked kind of a point of departure. Yeah. Even though I have never forgiven Zubin for the name, I have to say that this model is really, up to this point in machine learning, what we were doing is we were taking models that had been invented in statistics, and we used them and reused them and put them together in different ways to create new models. And then what Zubin and Tom Griffiths did here when they invented this model, they said they looked at a problem for which the right Bayesian nonparametric model did not exist, and so they just built their own. Yeah, and that was the starting point of a new way of, in my opinion, of doing Bayesian nonparametrics in machine learning. Okay, so what we do here is we look at the following problem. We have think of a clustering problem. Yeah, in a clustering problem, the assumption that we make is that each point belongs to exactly one cluster. And now, what we would like to do here is we would like to also group data points, but we would like the clusters, we would like to permit the clusters to overlap. So a point should not be exclusively assigned to one cluster. It should be possible for a point to be in several clusters at once. Now, how do you express it? So there's there actually have been some models for that in in the parametric literature before, where people basically use clustering models to express something like this. So they modified finite mixture models, and the way it's then being expressed is that you have, instead of having a point assigned to a cluster, you have something like assignment probabilities, just like a DEM assignment probability matrix. Yeah, so a point is assigned to this cluster with weight 0.5, and to the next one with 0.3, and they all add up to 1. But that is really arguably not what you want to model, right? Because it means that, for example, a cluster, a point that is only in one cluster will enter in that cluster with weight 1. A point which is in several clusters will enter into the same cluster only with 0.3 or something like that. Yeah? So what you would like to have is rather an on-off switch, am I in that cluster or not? And that is exactly what this model is. Okay. So the way the model works is it uses a binary matrix, yeah, and it's n by k. N are the number of observations, so we have observations in rows, and then we have clusters in columns. And this is often used as a model for, as a latent feature model. In that case, these clusters are features, so the point can exhibit a feature or not, and you can turn it on or off. Yeah? By putting a 1 in the matrix, 1 means the feature is on, 0 means it's off. Yeah, so we have these variables n, x, and k, which can take value 1 if the observation is in the cluster or has a feature, or 0 otherwise. Yeah. Okay, and now the generative model for this process, so corresponding to this two-part formula we saw before for the Dirichlet process, for this model it looks like this. The first data point is assigned to Poisson alpha clusters, Poisson alpha features. Okay, so a Poisson distribution is a distribution on non-negative integers. Yeah, so we draw a number from this, say 3. Okay, and so the first data point exhibits 3 features. 3 features are on, and that means it gets 3 1 entries in its row in this matrix. And now the next data point comes in, and just as in the Dirichlet process, we would like to have a device which can either assign new features or assign the point to features that we have already seen. Yeah? And that is what we do here. So with a probability proportional to the number of times the feature has already been observed. Yeah? So features that are exhibited by a lot of data points are more likely. Proportional to the number of times the feature has already been observed, we turn it on. And then we can also, once again, create new features. And you see there's a very similar dynamics in this model as more data points come in. This here, I mentioned before that for the Dirichlet process to get exchangeability, it's really crucial that the probability of seeing a new cluster decays when you see more and more points. And here you have a similar thing. As the number of data points increases, the probability of seeing new features once again decays. Yeah? So here, in terms of the mean of this Poisson distribution, which shifts towards 0, and here, large groups become more small. Yeah? And it turns out that once again, that gives you exchangeability, actually. So it gives you an exchangeable distribution over finite sets, yeah, which are these so-called dishes or clusters or features or whatever you want to call them. And the interpretation is observation is in n is in cluster k if customer n tries dish k. Yeah? So this is basically modeled. What they did at the time is they took this Chinese restaurant analogy, which was simply the way that people were thinking about the Dirichlet process or the Chinese restaurant process, and modified it in a way to explain this model, yeah, to make it more accessible. Okay, now there's an alternative description of this model, and that works as follows. So we can generate this matrix in a different way by two-stage sampling. Yeah? So we first sample. Think of the Dirichlet process again. We first sample the mixing measure, and then we sample from the mixing measure. We get a partition. This partition is distributed according to something called the Chinese restaurant process. The thing corresponding to the Chinese restaurant process is this thing here. Yeah? And now we can ask what would correspond to the Dirichlet process in this model. Okay? So that means we need to have some kind of two-stage sampling procedure. And for this matrix, we can do that in the following way. We simply sample for each column, so for each feature, we sample a probability of occurrence from a beta distribution. which has to be parameterized in a certain way. So this gives us each of these w's is a value between 0 and 1. And then we simply go down through this row and do IID coin flips with this probability here. Yeah? So we flip a W1 coin for each, independently for each entry in this row. And each time a 1 comes up, we enter a 1 into the matrix. Okay? So points, the data points are independent within, conditionally independent in the rows, given these W's. Okay? All right, and you can see here that in the parameterization of this beta distribution, we have alpha over the number of columns, over the number of features that we have seen so far. And now, if we ask, okay, if we do this in an infinite model, then we have to take some form of limit of this as k goes to infinity. So we have to ask what is the right limit object here. And turns out that what you can use here is something that was independently developed in Bayesian Nonparametrics for a completely different purpose, and that is called a beta process. So look at this here, that looks kind of familiar, right? So what we have here is, once again, a weighted sum over Diracs, yeah? But now the weights are between 0 and 1, so we don't have a normalization constraint, they don't have to sum to 1. So what we see here is, this is, if we make this quantity random, then it's a discrete random measure, but it's not a discrete random probability measure. Okay? This is a measure, but it's not a probability measure. Because this here doesn't have to sum to 1. Okay. And the interpretation is that this here is something corresponding to the atom locations in the Dirichlet process. Yeah, this phi k, the location of this Dirac, but then here the wk are separate weights for these beta distributions. Yeah, it's very simple. Okay. So basically, if you think back to the Definetti theorem I showed you in the beginning, where we said exchangeability gives us this decomposition of the integral, where we integrate, we have a prior distribution Q that we're integrating against, then we have an infinite product over a distribution, and that gives us some exchangeable distribution on the other side of the equation. Yeah? In the case of the Dirichlet process, the exchangeable distribution on the other side of the equation is a Chinese restaurant process, and the prior is a Dirichlet process. Here, the exchangeable distribution on the other side of the equation is this infinite buffet process, and the prior is this beta process. Yeah? Okay. All right. Good. I think I'm going to stop here, and then tomorrow I'm going to talk about how we can construct models that are a bit more general than these models that we have seen, which all correspond in some way or another to a random discrete random. Okay. Thank you very much. Can we take some questions, or yeah? Where do you just integrate? What do you mean by just integrating? Sorry?
Just sample. I mean, in terms of samples. I know you can integrate, but you can put a file there.
Yeah. Okay. All right. I see that everybody wants to have lunch, but I'm trying to answer the question anyway. Okay. So the question is whether it's a good. If I understand correctly, whether it's a good way, it's a good idea to put a prior distribution on the alpha parameter of the Dirichlet process. Yeah. Okay. So I mean, essentially, there's two things you can do. You can either fix the alpha and use that, or you can try to, in some way, learn or estimate the alpha. And now if you want to do that in a fully Bayesian way, then you have to put a prior on it. Right? If you want to estimate it, you have to put a prior on it. You could also do it in some mixed Bayesian, non-Bayesian way by optimizing with respect to the alpha or cross-validating. Yeah, that is another possibility. And I think you were asking about integration, so whether you should integrate out the alpha or whether you should sample.
No, I mean more if you are guaranteed that you preserve the characteristics. I mean, if you put naively, if you put an unnormalized parameter on alpha which concentrate all the mass around 0, I might be worried that I don't get the scaling in the number of clusters. I mean.
Okay. Okay. So you're saying if I put on a prior like a gamma 0.01 prior, which is very strong at 0 and then decays very rapidly.
Yeah, but that's what I usually see people do.
Yeah. So okay. Right. So you have to be aware that if you put a prior on the alpha, it doesn't solve your problem. It's another prior assumption, right? What it does is it softens up the dependence of your solution on the alpha, right? If you the model is you allow the model with a limit set by the prior to change, to adjust the alpha if you got it wrong. That's essentially what you're doing. So it's not, it's a choice of prior type problem, right? Of course, the specific case, what you mentioned, these gamma priors that people like to use on all kind of scale parameters, which are often basically where you try to make it as vague as possible by pushing it as much to 0 as possible, because it's like the 0.01 gamma prior. That is a whole problem in itself, yeah. And there's quite a lot of work in the literature where people discuss why these priors make sense and don't make sense. Yeah. But that is a slightly different issue. But it's probably not.